Hey Peyton,
Um,
how are you?
I'm doing good. How are you?
I'm doing fine too. Are you familiar with the Diels auto reactions now or electrocyclic reactions?
I actually have no idea what Felix talked about today.
Oh, what did he like what reactions did he go over today?
Oh, wait, let me
Uh-huh.
pull up my notes.
Yeah.
I think he went over the federal crafts acetylation,
Mm.
and then
Oh,
also like other
yeah, like the
fatal
electrophilic
crafts.
aromatic substitutions like alkylation, acylation, and the other ones like nitration, sulfonation,
Mm-hmm.
and halogenation. Um, yeah, so let's go over that. Did you go over aromaticity and how to tell if a molecule is aromatic or not yet? Like if it's anti-aromatic, non-aromatic.
I went over some examples, but don't think I fully mastered it.
Okay, yeah. Let's go over some examples of that. Uh-huh. Okay.
Do you?
So to determine if a molecule is let's say aromatic versus non-aromatic versus anti-aromatic, it would be this table that I use right here. So to be considered either aromatic or anti-aromatic, the molecule has to fulfill these three conditions. Let's call them conditions A, B, C. They have to be cyclic, they have to be planar, and they have to be fully conjugated. Right? And let's say that the molecule does not fulfill one or more of these conditions. So let's say a molecule is missing one plus conditions. Then that would mean that that molecule is going to be automatically be considered a non-aromatic molecule. Now, if the molecule has all three conditions, it could either be um, aromatic or it could be anti-aromatic. And to tell the difference between them, we use something called Huckel's rule, which is like the 4n electrons or 4n plus 2 electrons. Aromatic would have 4n plus 2. Anti-aromatic would have 4n. And then non-aromatic, it doesn't matter. It could be 4n plus 2 or 4n. Because it doesn't matter how many electrons the non-aromatic molecule has, as long as it like does not fulfill at least one of these conditions, it's considered non-aromatic automatically.
I think Leavens, instead of using like 4n or 4n plus 2, she's
Mhm.
like it's a
It's harder.
degree
Yeah.
of unsaturation odd or even. Is that a valid
Uh-huh.
method or is that
Yes.
like
That is the better method that I use. Like the
oh
way
okay
that
okay.
you learn it in Helix class is for n plus 2 versus for n, but I like to think about it as in terms of odd pair of electrons or even pair of electrons. Anti-aromatic is going to be a even pair of electrons, whereas the aromatic is going to be an odd pair of electrons.
Oh I see. Thank
Yep.
you.
It's gonna make more sense when we do more practice problems. Like the pairs of electrons during resonance are like how many arrows we could draw when we do resonance structures. Basically. Like that would make it fully conjugated. So now, let's look at a common one, which is benzene right here. This benzene molecule here is cyclic. It is planar because all of the atoms there are sp2 hybridized, and it is fully conjugated because it could do resonance all around the ring like that, making it fully conjugated. Right. Okay. So now, because we know that it fulfills all of the three conditions here, it is cyclic, planar, fully conjugated, then we see how many pairs of electrons are doing resonance with each other. We saw that we were able to draw 3 pairs of electrons, which is an odd pair of electrons, and that would make it aromatic. Right, so this benzene molecule here is aromatic. Any questions on that?
No, I think that makes sense.
Yeah. Now the stability of these are gonna be like the aromatic molecule is the most stable. Right, so the arrows I'm gonna draw here in black is gonna be stability arrows. So aromatic is the most stable, then non-aromatic, and then the least stable is gonna be anti-aromatic. Right, it has to do something with the molecular orbitals, but this is gonna be more multiple choice question. Right, so he's gonna give you a whole bunch of molecules, and he wants you to choose, let's say, the most stable molecule or the molecule with the least energy, and energy is gonna be in pink, let's say, right? Um, Aromatic molecules have the least energy, and then anti-aromatic molecules has the most energy because it's the least stable, right? Energy and stability are inversely related to each other. Stability inversely related. Okay. Nice. Hey, Elysia.
Hi, Brian. Can you hear me?
Yes, I can hear you. Uh-huh.
It's been a while.
I know. It's been like the what was it, 2-day weekend of
Yeah.
President's Weekend? You know, yeah. Right. So yeah, we're gonna keep going with this chart right here. This is anti-aromatic. Now let me give you more molecules here to work with here, right? And let me give you, let's say, let me give you these ones here. I'm gonna give you a whole bunch, and we're gonna work them through them together. And after this, we'll go over electrophilic aromatic substitution reactions with all those reactions like Friedel-Crafts, alkylation, acylation, nitration, sulfonation, right? Okay, so that's, whoa, that looks weird. Boom, 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 boom. H, okay, that's one of it. Just give you some weird examples as well. Case. Whoa. Okay. Hey, Crystal. The last two here, I'm gonna give you some exceptions. Okay, so since everyone here is in 1team B, I'll give you a whole bunch of molecules here, and I want you guys to determine whether or not these molecules are aromatic, anti-aromatic, and non-aromatic. So let's go over them briefly again. This is just a way to classify what the molecules are. Aromatic molecules are the most stable. and then non-aromatic is the second most stable, and then anti-aromatic is the least stable. To be considered either aromatic or anti-aromatic, the molecule has to fulfill all three of these conditions. They have to be cyclic in a ring. They have to be planar. Everything is sp2 hybridized or flat and planar. And they have to be fully conjugated, meaning that they could do resonance all around the ring. Right? An example would be benzene. Right? Benzene here is cyclic. It's a ring. It is planar. All of the atoms here are sp2 hybridized, which is flat and planar, and it is fully conjugated. We see that we could do resonance all around the ring. So it fulfills all three conditions. Now, once it fulfills all three conditions, to determine if it's aromatic or anti-aromatic, we look at how many pairs of electrons are doing resonance with each other, aka how many arrows do we see here? We see 3 arrows, which is an odd pair of electrons, which an odd pair of electrons would give us an aromatic molecule. You could think of it as 4n plus 2 or 4n electrons, but I like thinking of it in terms of odd pair or even pair of electrons, right? Now, if the molecule is missing one or more conditions, like let's say it's not cyclic, or it's not planar, or it's not fully conjugated, it could miss 2 as well, like not planar, not cyclic, or it could miss all 3, but at least one condition is missing, it's going to be automatically considered non-aromatic. It doesn't matter how many electrons it has, right? It's automatically non-aromatic. Okay, um, so let's take a look here. We could do this in order, like Peyton can do this one, and then Elysia, and then Crystal can do the next one, and then don't worry if you guys get stuck, just let me know, and then I can guide you guys through it. So let's start with Peyton. How would you analyze this molecule here? What would you look at first?
The conjugation.
Conjugation. So on the exam, helix will not give you the pairs of electrons, but there is an invisible pair of electrons here.
Yes.
We see that it could do conjugation all around the ring. And so it is cyclic, it is fully conjugated, and it would be planar as well. Because this is a 118A question. What is the hybridization of this nitrogen atom here? This is like one of the trick questions in 118A.
I think that's more like a Jenkem question, but is it sp2?
Yeah, it's sp2, right? It looks sp3, right? Because it has 4 bonding groups, like the 1 pair of electrons and 3 single bonds. But it's not sp3, it's sp2 because this pair of electrons here can do resonance, right? And if it could do resonance, it's going to be sp2 hybridized. Right? Let's say the double bonds were not here, and the lone pair of electrons here cannot do resonance. Then that nitrogen would be sp3. Right? If this lone pair of electrons cannot do resonance, it would be sp3. But because it can do resonance in the ring, then it's sp2. Okay, now if it fulfills all 3 conditions, how many pairs of electrons do you see are moving around here that are fully conjugated?
I see 3.
Yeah, 3, which is an odd pair. An odd pair gives us aromatic molecule. So this molecule here is aromatic. Okay, nice. Any questions on this one? Okay, let's move on to the next one, Elysia. This one here is a bit more difficult. Let me give you a hint here. How many pairs of electrons that are hidden do you see here, Elysia? Like are hiding from you?
Is there the lone pairs from nitrogen?
Yep, it is. There is 1 lone pair of electrons on nitrogen right there, right? But this lone pair of electrons on nitrogen here is not included in the resonance structure of the ring, right? The reason why it's not included in the resonance structure of the ring is because this nitrogen here that has the pair of electrons is already double bonded. If it's already double bonded, then its p orbitals are already taken. So let me draw that out there. Like the p orbital between this nitrogen atom and this carbon atom here, they are overlapping with each other already to create that double bond right there, right? Because double bonds are like a it's considered a pi bond, which is a network of adjacent p orbitals like this, right? So because of that, this pair of electrons here, because it's not in the p orbital, it cannot do resonance. This is in an sp2 orbital. That pair of electrons there is in an sp2 orbital, which cannot do resonance. right? So we would not consider that pair of electrons at all when we count how many pairs of electrons are doing resonance. Everything is kind of messy right now, so let me redraw this like this. Right, so there is a pair of electrons on that nitrogen right there, but we don't count that when we are counting how many pairs of electrons are doing resonance, right? But it is cyclic, it is fully planar, and it is conjugated, fully conjugated. And we see that there are how many pairs of electrons doing resonance here? Around
6.
the ring? 6, yes. 2, 4, 6 electrons. Which is, you could say 4n plus 2. If you plug in n equals 1, then that would give you 6 electrons. So that follows the 4n plus 2 rule, which is aromatic. You could do it that way, or you could think of it as how many pairs of electrons are moving. Like how many arrows would you see drawn here are moving, which is 3 arrows, 1, 2, 3, odd pair of electrons. An odd pair of electrons would give you aromatic, right? Based on this table here, odd pair of electrons, aromatic, even pair of electrons, anti-aromatic. Or you could do the 4n plus 2 or 4n, whichever way makes sense to you. Okay. Now let's move on to the next one. Crystal.
Okay, well, first of all, the nitrogen has the lone pair.
Yep.
Mm, I think. Let me think. I think it is conjugated fully.
It is fully conjugated. Right. So that condition satisfies.
Mhm.
It is fully cyclic and it is fully planar
Yeah.
as well. So all three conditions are fulfilled.
2, 3. Okay, there's 5 pairs of electrons.
Yeah. 1, 2, 3, 4, 5. Odd pair. Aromatic. Nice. Okay. Yeah, so that's how we do that one. And we count this pair of electrons of nitrogen there because this nitrogen here is not double bonded, right? It's single bonded. So we can count that because that pair of electrons is in the p orbital, which is doing resonance with all these other p orbitals here in the conjugated system. Okay. Yeah, p orbital resonance. Okay. Let's move on to the next one. Peyton.
I think they're all fully conjugated.
Fully conjugated, cyclic, and planar. So all three conditions
Yeah.
are fulfilled.
Then I see 6 pairs of electrons. So
1, 2,
you
3,
are
4, 5, 6.
even.
Yep, even pair of electrons, which would mean what kind of molecule this is?
Anti-aromatic.
Yep, anti-aromatic. Nice. Okay, now that's good. Let's move on to the next one, Elysia.
So we have 2 invisible hydrogens, and then I know that well, it's not fully conjugated.
Not fully conjugated because of this sp3 roadblock. Right, that sp3 roadblock is blocking resonance, making it not fully conjugated. Right, it is cyclic. Right, all this is in a ring, but it's not fully conjugated and it's not planar because of this sp3 carbon right here that has a tetrahedral shape with a 109.5-degree angle. So not cyclic. Well, it is cyclic, but it's not planar and not fully conjugated. So that would make this automatically non-aromatic molecule. Yeah, nice. So be careful of this sp3 roadblock hidden carbon right there, right? Because that would make it non-conjugated, non-cyclic as well. Okay, let's move on to the next one, Crystal.
I'm pretty sure this is aromatic. Because it's fully conjugated and all of the above.
Yep. Cyclic, fully conjugated, and planar. And it has 3 pairs of electrons, odd pair. 1, 2, and that invisible one right there on that carb anion. Okay, nice. Next one, Peyton.
I think it's not fully conjugated.
And would you say this one here is the problem, that it's not making it fully conjugated?
Yeah.
Yeah. So let me put the positive charge near here. There's a carbocation on that carbon.
Oh, I see, I see.
So this carbon here is sp2 hybridized with a p orbital, and that can do resonance with the double bond like that, right? Because we could shift the double bond over to make a double bond here, which would then create a positive charge here, and then we could do more resonance like that, creating a positive charge there. So all of these carbons here are sp2 hybridized with a p orbital that can do resonance with each other. So it is fully conjugated here.
Oh, I see, I
Yep.
see.
Mm-hmm.
So it satisfied the three conditions, and it's an odd pair, so it's anti-aromatic.
Oh, two pairs. One, two. Two pairs.
Oh,
Yeah.
yeah. So
Yeah,
it's
okay.
even.
Yeah, even
And
pair.
then it's anti.
Yeah, anti. Right. Anti. Nice. It would be odd in the last example because we had three, one invisible pair of electrons here, and two, three there. That's three, odd pair, aromatic. It's okay. I also messed up like figuring that out too when I first learned these problems because it gets so confusing. Like I thought that positive charge was also a pair of electrons, but keep in mind that this positive charge here shows the electron deficiency. It's missing electrons. There's an empty p orbital here. There's no electrons there, so that does not count as a pair of electrons. But these double bonds here do count as a pair of electrons like that. Okay, so carb anion, full p orbital with a pair of electrons, that does count. Carbocation, empty p orbital with no electrons there, so there's no electrons there, but it can still do resonance with these double bonds here like that. Okay, let's move on to the next one, Elysia.
I don't think it's. I think it's not non-aromatic because it's not fully conjugated.
Yep.
And it is.
Oh, shoot. Yeah, it's not planar as well.
Yeah.
Because of these tetrahedral sp3 carbons with 109.5 degree angle. But it is cyclic, but it doesn't fulfill the fully conjugated and planar. Okay, so it is automatically non-aromatic.
And I heard those are very unstable.
Non-aromatic molecules are relatively stable. Like they're like the normal molecules you see, like the alkane, cyclopentane, cyclohexane. So non-aromatic molecules, if they exist by itself, then it is like relatively stable. Aromatic would make it even more stable, but anti-aromatic are the ones that are very unstable. They don't want to be anti-aromatic at all.
Okay.
Right, but there is another reason why like this specific non-aromatic molecule is very unstable. Can you think of that specific reason why this one here is very unstable? It's something else.
The negative?
The negative charge. So yeah, that's one reason, right? That's one reason why it's like unstable. There's a negative charge on the carbon. But what about the molecule's geometry do you see here, like shape? What do you see here? Something about, let's say, strain. What kind of strain does it have? This is for 1 in anything. It's okay if you forgot. 1 in anything.
Yeah, I forgot.
How many membered ring do we have here?
It's a 3-membered ring.
3-membered ring, right? And that's very unstable. It has a lot of ring strain and bond angle strain.
Yeah.
Yeah, right. Because these sp3 carbons, like we said, has like a preferred bond angle of 109.5 degree angle, but these bond angles here are forced to become 60 degree angles, which is way less than 109.5 degree angle. So that's a lot of bond angle strain, a lot of ring strain right there. Okay. So that's why this molecule here specifically is very unstable because of that ring strain, bond angle strain.
Okay.
Okay. That's gonna be non-aromatic. Let's move on to the next one, Crystal.
So it is fully conjugated. It's planar and it's cyclic. There are 6 electrons, so it's aromatic.
Yeah, 6 electrons, 4 n plus 2 electrons, or odd pair of electrons, aromatic. Nice. Okay, no pairs of electrons on this carbocation because it's an empty orbital, missing electrons. Okay, nice. Now this one here is a little bit tricky, Peyton, because when you see a carbonyl like this, carbon double bond oxygen, it's not part of the ring. So before you do anything, draw out the resonance structure where we pop the double bond onto the oxygen, giving us this resonance structure right here. And we're only going to be focusing on this highlighted part of the molecule right there. Okay, so now if we focus on that, what molecule would this be? Aromatic, anti-aromatic, or non-aromatic?
So it is fully conjugated, and I see 2 pairs of electrons. I mean, not two.
Yes. Uh-huh.
So
Right.
it would be even and anti-aromatic.
Yes, correct. Yes. Got it? Nice. Yeah, so that the tricky part here for this molecule is that it's carbonyl right here. If you see carbonyl, this carbonyl carbon in pink will have a positive charge. Okay. Okay, now these last two here, right? It is cyclic. It is fully conjugated, but it is not planar. Right? This one on the right here that looks like a stop sign is a boat shape. Right? It looks like this. This one right here is not planar because the carbons in the middle right here are very close to each other with a lot of steric hindrance. So one hydrogen is going to go up on a wedge, one hydrogen is going to go down on the dash, and that would like shift this up and shift this down, making it non-planar, right? And because these two are non-planar, they are going to be considered non-aromatic because it does not fulfill all three conditions. Right, so these are the two most common non-aromatic molecules you see that are because it is not planar, and that's the hardest one to see, right? Like it is fully conjugated, it is fully cyclic, but it's not planar, right? In most examples that you see on the exam, like you could assume that the planar molecule is there if it's cyclic and fully conjugated, but just keep in mind of these two molecules here, this like stop sign looking thing and this weird looking steric hindrance thing. Right. Yeah, and that might come up as a explanation problem, like a student thinks that these fulfill all three conditions, and this one would be, if it's even pair anti-aromatic, this one 1 2 3 4 5 odd pair aromatic, but why is it not aromatic nor anti-aromatic? It's because of this planar condition that is not fulfilled right there. Okay, any questions on aromatic, anti-aromatic, and non-aromatic before we move on? Okay. Hey, Wiley.
Nope.
Yeah. Okay. Now let's move on to electrophilic aromatic substitution, which is the benzene reactions. They are also known as EAS reactions. Electrophilic aromatic substitution. EAS reaction. Okay. So your benzene here is going to be your nucleophile. There's going to be a lot of reactions for this type. This is a mechanism, electrophilic aromatic substitution, and there's 5 different reactions for it. There's halogenation. There's nitration. There's sulfonation. And then there's the 2 Friedel-Crafts reactions. Friedel-Crafts alkylation and Friedel-Crafts acylation, which are the hardest ones here. Right. Friedel-Crafts alkylation and Friedel-Crafts acylation. Okay. Now, depending on what reaction you use, your electrophile is going to be different. If you use halogenation as the reaction of this EAS mechanism, the electrophile is going to be like a halogen, like chlorine or bromine, right? And we're going to attach a chlorine or bromine onto the benzene ring. Chlorine or bromine. Nitration is going to add a nitro group, NO2, to the benzene ring. Sulfonation is going to add a sulfonate group onto the benzene ring. Phenolcal's alkylation is going to add an alkyl group, R group, onto the benzene ring. And Phenolcal's acylation is going to add an acyl group or carbonyl group with a R group attached to the benzene ring, right? So let me give you guys the general mechanism of this right here. Very general mechanism. It's 3 steps. The first step is to form your electrophile. That's the hardest step of the mechanism. Form the electrophile because it's different for all the reactions. Once you have the electrophile, however, steps 2 and 3 would be very similar to each other. The second step is to do addition. Third step, elimination. Right? You could think of it as like addition would break the aromaticity, and elimination would reform the aromaticity. Okay. Now let's look at a very general mechanism here. Let's say we have this empty benzene ring with no groups attached to it, and some sort of electrophile. Like let's say our first step, electrophile forming, is done, right? And it's gonna be different for all of the reactions that we went over: halogenation, nitration, sulfonation, and the diffuse reactions. Like the mechanism to get to this electrophile is different, right? But let's say we have it already, and we'll go over like specific ones when we go over there. But I want to talk about the general thing, what's going on here first before we do that. Okay. Now, once we have the electrophile, we're gonna do addition. We know that this benzene here has a lot of electrons in them, right? So we know that all of these carbons here are nucleophilic because you could think of it like this. We could push this double bond onto that carbon right there, which would give us this resonance structure right here, right? And we see that this carbon here with the full negative charge can be considered our nucleophile, right? And that could be the same for all of these carbons here. In this case, it doesn't matter which carbon is the nucleophile. We could choose a random one. So if I star that carbon right there, I'm going to have that star carbon attack this electrophile right here, right? And when that happens, this is the new bond between the starred carbon and the electrophile right there. This double bond here stays the same, that double bond stays the same, but this double bond right here is no longer there because it's used to grab that electrophile, to make that like neo bond between this starred carbon and electrophile right there. And because that double bond is no longer there, this carbon here lost a bond, which became a positive charged carbocation right there, right? Before we see that it was a happy, stable, aromatic molecule, but now after this addition step, it's now non-aromatic because of this sp3 roadblock. So it is less stable now, right? It is less stable than it used to be, making it have more energy, right? This has more energy than this because it is less stable. Okay, so that's the addition step. The third step is to reform the aromaticity, and this is going to be an E1 mechanism, right? Where I'm going to explicitly draw out the hydrogen here of that star carbon and some kind of base. The base is going to be different depending on what reaction you use. It's going to grab that hydrogen. The bond between this hydrogen and star carbon here is going to move to make a double bond right there, to remake our benzene ring, to reform our aromatic ring. Right? And the electrophile is still there. Right? And you could draw the side product base with the hydrogen if you want, depending on what the reaction is. Yeah, usually the base is negatively charged, so let's draw the negative charge base right there, grabbing this hydrogen, which becomes neutral. And now it is aromatic again, making it have less energy again and stable again. Right? So this first step here that we did was addition. The second step here was elimination. And specifically, this was like an E1-like mechanism because we had the carbocation right here. Okay. Any questions on this mechanism? Okay. Now, I'm gonna show you guys halogenation mechanism here, and then we'll work through the other ones one by one. Right, so let's see here. Let's say we have this benzene ring, And the reagents that you're going to see are X2, where X can be chlorine or bromine. And our catalyst here is going to be AlX3 or FeX3. And what that's going to do is that's just going to add the X on the benzene ring, the halogen on the benzene ring like that. Okay. Let's give you a specific example. Let's say we have CO2 reacting with AlCl3. That would add a Cl, chlorine, on the benzene ring like that. So that's how you predict the product quickly. It's just adding that chlorine there on the benzene ring. Now the mechanism here would be like this. We said earlier that there are 3 steps to the mechanism. The first step, form our electrophile. Second step, addition, once we have the electrophile. And then elimination to restore the aromaticity after, right? Now the first part here, forming the electrophile, is the hardest because it's different for all the different reactions. I'm going to draw out the CO2 like this, and the AlCl3 like this. Okay. This aluminum here, it's one of those weird atoms like boron or iron. It has 3 bonds, right? So I'm going to draw this out like this actually to show you what's weird about this aluminum. This aluminum here has 3 bonds, aka 6 electrons. So it's missing the octet row. It is missing 2 electrons. It has an empty p orbital. But it is not positively charged, right? Because usually we see that when a carbon, let's say for example, has only 3 bonds and is missing 2 electrons, it is positively charged. It has a carbocation like that. Right. Hey Jenna. So because of that, this aluminum here has a empty p orbital, which is going to be our electrophile, right? So one of the chlorines here is going to attack that empty p orbital and give us this substrate and leaving group right here. Where aluminum with 4 bonds is going to be negatively charged. And it's like a boron, right? Boron with 4 bonds is negatively charged. This chlorine here with 2 bonds is going to be positively charged. So think of this whole thing here as your good leaving group, and think of this here as your substrate, your electrophile. That's our electrophile right there. And that's the end of the first step. Let's do the second step now, where we do the addition step, right? Where we bring in that benzene, and then we bring in the electrophile that we formed in the first step, right? Let's say we choose that carbon as a nucleophile. That's going to attack this chlorine here and then kick out that whole leaving group right there and give us this intermediate here. Okay, with a Cl, AlCl3 minus. Okay, now that's the addition step where we came from an aromatic ring to a non-aromatic ring. Now the third step, elimination here, is to do reforming the aromaticity. So our base here is going to be this chlorine atom here of the AlCl4 minus. That chlorine atom wants to leave as a negative charge, so just think of that as a negative charge. Even though the aluminum here has a negative charge, it's not going to attack the hydrogen, right? It's going to be the chlorine here with the negative charge that's going to leave with the bond to attack that hydrogen, reform the aromatic ring like that to give us this benzene here, chlorine, and HCl gets formed. If I highlighted that chlorine in yellow, that's that chlorine in yellow right there. This blue hydrogen is that blue hydrogen right there. And we reform our metal catalyst AlCO3 right there. Right? That's why this is called a metal catalyst, because it gets reformed in the mechanism. So that is the mechanism for halogenation right there. Any questions on this mechanism? On like either the first step, second step, or third step? Okay. So I'm gonna move on to like, let's say maybe 128B or 8B. But for 118B, like all these reactions here are gonna follow the exact same 3 steps of the mechanism here. First, form the electrophile. Second step, addition. Third step, elimination. I would say halogenation, nitration, sulfonation would be like the easier ones. The harder and longer ones would be the Friedel-Crafts ones, like Friedel-Crafts alkylation and acylation, especially alkylation because of the hydride shift, concerted shifts, and things like that, right? Because that would change up what the product you predict to be like. Yes, so we could go over that in other office hours like next week, but for now, let's. I'm gonna move on to 128B and 8B. Okay. So Wiley or Jenna, did you have any questions or topics you guys wanted to go over today?
You want to review the thing or something?
Oh yeah, let me see. Yes, so that reaction that you sent me, we did not go over in 118, but it looks very similar to the aldol condensation, aldol dehydration. So based on that, I'm just gonna show you what I think it is, but I'm not entirely sure. Right. Horner, Wadsworth, Emmons reaction. Okay, so we're gonna have this phosphorus attached to a double bond oxygen, OET, OET, boom, boom, OET, boom. Okay, and then the first step is a strong base, and a strong base example would be NaH. Second step is gonna be aldehyde, like this. Okay, and that gives you boom, boom, OET, like that. This alpha, beta, unsaturated carbonyl. The reason why the name is like this is because this is our carbonyl here, carbon double bond oxygen. This is the alpha carbon, that's the beta carbon. Between the alpha and beta carbon, there is a double bond, also known as an unsaturation. So that's why this is called an alpha beta unsaturated carbonyl. Alpha and beta to the carbonyl right there. A short name for this would be an enone. Right.
Oh, okay.
Enone, right. Because like in most cases, like there's an alkene here, and usually this is a ketone, but this is not a ketone, this is an ester. But just imagine that's a ketone. That's where the enone shorthand comes from. An alkene next to a ketone. But is this one here is not very accurate because it could be a ester just like this.
Yeah.
Okay. Now, the first step, H minus strong base, is gonna look for the most acidic hydrogen. The most acidic hydrogen is gonna be on the alpha carbon right there. Like that's the most acidic hydrogen right there because it's in between. The resonance, right? When we draw the conjugate base, that negative charge of the conjugate base can do resonance like that. That's why it's the most acidic hydrogen, right? So let me grab that hydrogen and generate the enolate ion. The bond here between the hydrogen and carbon being grabbed is gonna make a double bond right here between the carbonyl carbon and alpha carbon, which would push this double bond onto the oxygen like that and give us this intermediate right here. Right, when I see this whole thing right here, I just think of it as a good leaving group, like bromine or chlorine or something like that.
Oh, okay.
OET. Now from here, we see the second step is an aldehyde where it has one random variable group or group. This enolate ion here, even though you see a negative charge on that O minus, that's not the nucleophile. The nucleophile is actually this alpha carbon right here that I'm gonna star. That's the nucleophile, right?
Okay.
The reason why is because I'm gonna draw out the resonance structure here, but for mechanism, you probably don't have to draw this resonance structure, but it will help understand why that alpha carbon is a nucleophile instead of the O minus, right? Even though there's a full negative charge on the oxygen. So when I draw that resonance structure out, we have a carbonyl again, and a full negative charge on that carbon atom right there. Now, if we look at these two resonance structures here, the major resonance structure is the top one, because the negative charge is more stable on the oxygen electronegative atom. And the minor one is at the bottom because the negative charge is less stable on the less electronegative carbon atom. And because this is minor, this is less stable, more reactive. Right? So that's why this carbon here with the negative charge is the nucleophile. The O minus here is already stable with the negative charge, so it's stable. It is gonna be unreactive.
Okay.
Right? Okay. So you could directly go to here by, just grabbing this hydrogen, and then instead of making a double bond there, we could give this carbon here where it's on a negative charge right away to go straight to here, which is more clear to see where the nucleophile is at, like that. Right?
Okay. Yeah.
Yeah. So let's use this here. Now let's begin the electrophile, the aldehyde we have in the second step, which is this carbon, which I'm going to dot like that. This star here is going to attack the dot, push the bonds to the oxygen, and give me this intermediate right here. Right, this is the star. I'm going to make the new bond between the star and dot like this. Right, that's the new bond between them. And the dot here is attached to an R group and a single bond O minus now. Right.
Okay.
But this star here is still attached to this good leaving group right there. That phosphorus, double bond oxygen, OETs, like that. OET. Okay.
Yeah.
Now I'm gonna rewrite this down here because I need more space to complete the mechanism. But from this intermediate right here, the next step is to protonate the O minus with some proton source. Like H plus, floating around somewhere, some proton source, to become neutral OH. Okay. Okay, yeah. The next step here would be to deprotonate the alpha carbon between the carbonyl and alcohol with another base, H minus.
Yeah.
Make the enolate ion. I'm getting confused because I know how to get to the final product, but I don't know how I'm gonna get rid of this later on. Because I do know how to get rid of the alcohol and put a double bond between the alpha and beta carbon, but I'm getting stuck on that leaving group right there. Right. Because let me just write this out here. I'm gonna abbreviate this as LG, so I don't have to keep writing that big group out. LG. Reform the carbonyl, shift the bond over there, kick out the OH. OET. So that's our final product that we want, but we have this LG attached to the alpha carbon. So we gotta figure out a way on how to kick that LG out. Let me see here. So
it's like it kind of like closes like the Wittig reaction. The
Wittig reaction. Because there's
the intermediate.
Oh, it does. It does. Oh, like the Wittig reaction. Oh,
yeah.
I see.
It kind of like the sort of square.
The square, yeah. It doesn't make a square with the carbonyl, here and the one phosphorus like that.
Yeah.
Okay.
Or
so did he go over the mechanism in class?
He just mentioned like, oh, you can do this, but like I had no idea. Like he just wrote it and then moved on. Like what?
Okay. Yeah. Yeah, that's weird. Yeah. So we know that we could do a Wittig reaction like mechanism because there is a phosphorus here, which can like leave somehow.
Okay.
That's a reaction like mechanism like that. Okay. Yeah. So the mechanism, don't worry about it because he didn't go over it. But to predict about it quickly, this is what I would do here. So let's say you have this group. Boom. And then this phosphorus with two OETs. OET, double bond. And you have first step, NaH, strong base. Second step, some aldehyde. To predict the product quickly, what I would do is I would star my alpha carbon of this reactant molecule, dot my carbonyl carbon of the electrophile aldehyde, get rid of this leaving group because that's not going to be there in the product. Make a double bond between the star and dot. So draw that right away. Star there, dot there. The star is attached to this ester. And then the dot will no longer have the carbonyl, but it will still have the hydrogen and the R group. But we could leave that hydrogen as invisible. So we have to draw that R group out though. But this hydrogen here is right there. That's invisible like that.
Okay.
Yeah,
You
so
like
that's how you
attach
could.
it kind of like sideways. The
Yeah, like I drew it sideways. I tilted it
Yeah.
sideways. You could have drawn
Okay.
it down like this as well. That could have
Oh,
worked as
okay.
well. That's the same thing, right?
Yeah.
And know that this is an alpha beta unsaturated carbonyl, and that's how you can confirm if you're like
Okay. Yeah.
having the right answer. Yeah. Okay. Nice. Hey Jenna, what are you going over right now in what 8B? Is it like the aldol condensation dehydration stuff, or what other things are you going over?
Yeah, it is. Let me hold on. We also, I think we're about to start carbohydrates tomorrow.
Yeah.
Because, yeah.
Yeah, that's a
She
lot.
just did. Yeah, I know. I saw the lab and I was so confused because I don't know why, but our labs, like the stuff we do, is material that we don't learn until the week after.
Oh my gosh.
Yeah.
Oh my
Yeah,
gosh.
that was in the lab.
The chair stuff? Oh my
Yeah,
gosh. 118A flashbacks.
I know. I hated that
Yeah,
stuff.
let me show you how to draw them, right? Today for the carbohydrates. So there's two types of chairs. There's this chair and there's this chair right here, right? But for carbohydrates, we're going to be focused on this configuration here, this type of chair right here. Okay, so I'm just going to focus on that for now. Don't worry about the other one because we won't worry about that for carbohydrates. Now, there's going to be two types of bonds for chairs. There's going to be equatorial, let's do axial first. Axial bonds and equatorial bonds. Axial and equatorial. Okay. So each carbon here is going to have one axial bond and one equatorial bond. The important thing to note here is that they will always be opposite from each other. Right? So if there's one axial bond that's going up, that equatorial bond has to go down from each other. And here's the way where how I remember like where the axial and equatorial bonds are going specifically. So let's start with the axial one because that's the easier one. Axial is just going either straight up or straight down. That's the axial one. Equatorial has some weird slant to it with some weird angle, specific angle. But let's focus on axial, which is just up or down. Okay. I always start at my top left corner right here. This carbon right here. This top left corner. That top left corner right there is always gonna be axial up. It's always gonna be like that. It's always fixed like that. You can't change that for chairs. Now, if you go to the next carbon, let's go down here. Let's go in the counterclockwise direction. It's gonna alternate. It's gonna go down like that. Go to the next carbon. This is gonna go up. Next carbon, down. Up, down. Right, so up, down, up, down, up, down, alternating between the carbons for axial.
So is it the ones that are like across from each other, they'll be opposites?
So this is not the opposite one yet because we didn't draw out the equatorial. This is just talking about the different carbons' axial bonds and the direction of the different carbons' axial bonds, right? Like if you just focus on this carbon's axial bond, it's going up. But if you focus on this carbon's axial bond, it's going down, right? We're not talking about the opposite bonds yet, like the opposite direction yet. We're gonna talk about that when we go over the equatorial bonds right here. Right.
Okay, but how do we know when they would go up or down?
Yeah, we know that this is gonna go up or down because this is always gonna be fixed like that. Like we cannot change that.
Oh, it's always gonna be like that. Okay.
It's always gonna be like this. Yes. You would have to worry more about like what groups go up, what groups go down if you do chair flips. Like if you flip this to the other chair like that. But we won't do that in this carbohydrate stuff, carbohydrate chapter. like I'm just showing you what you need to know for this carbohydrate here. Like it's always gonna be like
Okay.
this for this chair.
Got
yeah.
it.
Yeah. Now let's focus on this carbon here specifically, with the axial bond going up. If the axial bond is going up, the equatorial bond has to go down because axial and equatorial bonds are opposite from each other. Right. Now here's the hard part. Like, how do we know if the equatorial bond is gonna go down like facing like this way or this way? Which one looks right for you?
The one on the left.
Yes, equatorial. Think of it as going outside of the equator, right? Like this is the equator here, the molecule. It wants to go away from it, right?
Oh, okay.
That was like, that's a new word that I just came up with right now. But the word that I usually teach it is like this right here. Now we know it's going down. It's gonna be parallel to the second bond they don't touch. This is probably the more confusing way, but ignore the first bond right here, right? And then look at the second bond, which I'm gonna highlight right here. This is the second bond. Second bond. The equatorial bond has to be parallel to those two bonds like that, on the same direction like that, going down in those directions.
Oh,
Mm-hmm.
I like
So that's
that way too.
yeah, that's the way that I usually teach it. Like
Yeah.
it's more
Okay.
clear to see like where the direction has to go to. Like it's more clear cut.
Yeah.
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 Okay, so let's look at this carbon right here. Would this equatorial bond have to go up or down based on where the axial bond is going to right now?
It would go up.
It would go up, right? So to do that, what would you do? Like, what two methods would you do? Would you say go up this way, and which way would it be, and how do you tell the direction more specifically?
So it has to go away from the equator, so it would be the one on the left.
Yes, this one right here, right? So it's the one on the left right here. So now to help us tell like is it gonna go up that direction, this direction, or this direction, we then do that second trick that I just showed you. Ignore the first bond, look at the second bond. Parallel to those two bonds is that direction.
Oh, okay.
Yes. Now I'm gonna have you try drawing out the equatorial bonds for the 4 other carbons and send it to me when you have it, so I can check what you do. Because it does
Okay.
get a little bit weird. But just like focus on that, like where the first one is, ignore that, and then the second one, make
Yeah.
it parallel to that.
Okay, let me try it.
Yeah.
Hey, can I ask you a question, Ryan?
Yes.
Like a quick one.
Uh-huh.
I'm gonna send you something. Yeah. Like, could you just explain? It's the hydration of like aldehydes.
Hydration of aldehydes.
To make like the acetyl or whatever.
Yeah.
Here.
Yes. Oxygen
Like,
nucleophiles.
why is it easier to hydrate a aldehyde versus a ketone?
Oh, right. Okay.
My professor, he just explained, or like he just wrote it out, but he didn't like explain why. He's like, "Oh, we'll get to it later."
Oh,
I don't know.
okay. Yeah, he just said that.
Yeah.
Okay. Did he go over oh, he did. Yeah, like with the arrows here, like where water attacks and push that onto the oxygen.
Yeah.
The oxygen will have an O minus, but the O minus will eventually become protonated by acid source, like water, to become OH. So that would give you a hydrate or geminal diol like that. Let's say we have the ketone, same mechanism. Attack, push that up there, which will get protonated by proton source, OH. The reason why the aldehyde has an easier time forming a hydrate is because the carbonyl carbon is a better, stronger positive charge than in the aldehyde compared to the ketone. The reason why this is a stronger electrophile, it has a bigger positive charge, is because it has only one R group donating electrons to the carbonyl, whereas the ketone has 2 R groups donating electrons into the carbonyl, reducing the positive charge. Like this carbonyl is gaining more negative charge because it has more donating groups, whereas the aldehyde only has 1 donating group, right? What's even faster than a regular aldehyde is a formaldehyde, like that. Like this reaction here would be way faster because there's no R groups at all. What's even faster than that is this right here with the electron withdrawing group, right? Because this carbon here is actually withdrawing electrons from that carbon, even making it an even bigger positive charge like that, right? So the speed would increase from like going up in this direction right here. The slowest would be this ketone. Fastest would be this one with the electron withdrawing group, like that.
Yeah. Like ketones will basically never get hydrated, right?
Yes. Yeah, it is like 2% isolatable, it's 98% going to be in this ketone form, right?
Oh, okay.
Once you get into this aldehyde, like formaldehyde especially, and this one with the good leaving group, that's when you get like 98% hydrate.
Okay.
But if you're comparing this a regular aldehyde with one R group and a ketone, the regular aldehyde with one R group would be faster because it has the stronger electrophile, only one R group.
Yeah. Is there anything slower than, or like,
slower than
anything
this
slower
one?
than yeah.
Yeah, there is, right? Which is gonna be like when you
Is this more electronegative atoms attached?
electronegative atoms attached that are donating electrons into the carbonyl by resonance like that, because this electronegative atom here is actually withdrawing electrons from that carbon by induction because it's more electronegative, so it's actually like an electron withdrawing group by induction, so that does make it more positive charge by a point, right? But it is an electron donating group by resonance, and resonance is a stronger factor than induction. So because of that electron donating group by resonance, this carbon here is becoming like even a smaller positive charge, like that, right? Because it's gaining more electrons directly from that pair of electrons right there, right? So this group here is an electron donating group by resonance and an electron withdrawing group by induction, but overall we consider an electron donating group because resonance is stronger than induction in this case.
Okay.
Yeah. And that would make it even more slow. Okay. That's good. Okay. Nice. I see your thing, Jenna. Okay. Ooh, okay. So good thing I made you try it. Can you walk me through your thought process on how you got this one right here, Jenna?
Shoot, probably. Okay, actually, I was just looking at that one and I was like, wait, this kind of looks wrong. Would it be...
Okay, wait, so you drew it like down like this, right? Which is going down,
Yes.
right?
Yeah.
But what is the actual bond going to right now? Is it going down or up?
It's going down.
It's going down, so
that
that it should be up, right? Would it be up in this direction or this direction?
Away from the equator, so to the right.
Yes, to the right. And how would you find the specific direction that it goes to in this? Like, would it go here, here, here? Like, how would you find out the specific direction?
So like, the two bonds in the middle, I would just draw them parallel to that.
Like this?
Yeah.
Yes, correct. That's how we do that one. Nice.
Okay.
So this one here that you drew is going towards the equator and it's going down.
Yeah. Yeah, okay, that one was wrong. Are the rest right though?
This one here is right, because the axial one is going down, so that means equator has to go up parallel to the two bonds that they don't touch, which is this one and that one. So it is parallel to those two bonds. That's good. But these two here, let's look at them again. Can you explain to me how you got those two, Jenna?
Shoot. I did them because I was like kind of following a pattern in my head. But now I realize it's like going towards the equator, so I would have to draw it to the right.
Right, that's one of the problems, and there's one more problem here. Think about the direction of the equatorial bond.
It's going up, so I would have to point it down.
Yes, axial is going up, so you would have to point the equatorial down, right?
Yeah.
Let's look at this one here. Would it go down here or here?
The right.
The right, yes. Parallel to not that bond, but this bond and that bond. So it's be parallel going like that.
Yeah.
Like this, yes. Okay. And this one here is gonna go down as well. This or this way, left or right?
Right.
Right. Yep.
And then it would be parallel to those two bonds. So okay, it would be more flat.
Yes, like that. Yeah. So good thing we practiced that, Jenna. So you know the mistakes now, so that you don't make them in the future.
Yeah.
It's good. Yeah, it could be difficult, you know. Just practice drawing it more. Like just do it until you can, it's like, well, actually no, yeah, you have a note card anyway. You can just draw this in your note card and copy and paste it over.
Yeah, I was gonna say it doesn't seem too bad, and if it's fixed, then I don't really have to worry about like solving problems with it.
Yeah,
right?
Yeah, you don't have to, right?
Okay, that's good.
Right. But here's the thing about carbohydrates. Like the carbohydrates you can see is in this one right here, but the top right corner is gonna have an oxygen atom instead of a carbon atom. So you're gonna not have axial or equatorial bonds there. Right, so if you do the same thing, up, down, imagine this is gonna go up if that was a carbon. That would make this next carbon down, like that. Everything else is the same, copy and paste. Like that. But this oxygen atom here would not have any axial or equatorial bonds. Right there.
Okay.
Yeah, and that's the
That's
thing
it. Like
for carbohydrates.
everything else is the same.
Yeah, everything else is the
Like
same.
if it's something that isn't a carbon, it's not gonna have any equatorial or axial bonds.
Yes, a heteroatom, aka a non-carbon atom, will not have an axial or equatorial bond. Yeah.
Okay.
Uh-huh.
Okay, that makes
Nice.
sense.
Yeah, of course.
Okay. Thank you.
Yeah.
And also I'll upload the notes after this.
Yeah. Thank
I
you.
was gonna redo them because like I was just kind of scribbling through lecture because she was going so fast, but it doesn't seem like I think you'd understand it. Like it's not too messy, but I'll update it again when I rewrite them.
Okay, yeah, that's great. Thank
Yeah.
you, Jenna. Like your notes are like so detailed, and I rely on them for like the 8V content.
Yeah.
Yeah.
Okay. And I'll check my schedule and get back to you on like when.
Okay, yeah. If that time doesn't
do the
work, then we could
next.
like find another time that works for us too.
Okay.
Just let me know.
Sounds
Yeah.
good. Okay. Thank you.
Yeah. Good night,
Bye.
Jenna.
Thank you.